Okay. Okay. So, welcome once again to a new edition of the series of webinars organized by Alma, a newly formed Latin American Magnetism Association. In case you're interested in our activities, you can find us in the web, in our Facebook page, or email us to almamagnetism@gmail.com. You can also join us and participate in different activities of interest to our community, which can also be found in our newsletter. You can email us to be added to our distribution list. Our association is composed of different nodes, and we hope we can soon include representatives from other Latin American countries. So far, we have members from Mexico, Colombia, Peru, Chile, Brazil, and Argentina. I am very pleased to participate this year as the coordinator of the webinars committee, whose aim is to invite the speakers and organize the webinars. As you can see, all the nodes are represented by at least one member, conforming a very efficient and collaborative group. If you missed our previous webinars of this year or from 2020, you can find them in our YouTube channel, to which you can also subscribe. Today's talk will also be available in this site. These are our confirmed speakers for the upcoming webinars. We will take a winter break in July, but you can save the dates for August, September, and October. Our speaker for today is Sergio Rezende from Recife, Brazil, and his talk will be about Spintronics, fundamentals, and recent developments. As usual for our webinars, this talk is being streamed via Zoom and our YouTube channel. So without further ado, please let me introduce you to our chairman for today, who is Oscar Arnaz, a Colombian scientist from the Solid State Research Group, Physics Institute of Universidade de Antioquia, whose research interests are spintronics, magnetic and thermoelectric systems. Oscar will tell us more about our speaker of today. So Oscar, the floor is yours.
Can you hear me?
Yes.
Okay. Thank you, Maria. Thank you, Paula, for the introduction. Greeting everyone who join us today via Zoom and YouTube. It is my pleasure and honor to introduce Professor Sergio Machado Rezende in the Alma webinar today. Dr. Rezende has a very extensive curriculum vitae, and I will try to summarize the most important aspect. It is important to highlight that Professor Sergio is one of the most outstanding scientists in Latin America and the world for his contribution in magnetism and spintronic fields. I hope Professor Sergio apologize me if I have overlooked some aspect related to his curriculum vitae, okay? Professor Sergio Machado Rezende was born in Rio de Janeiro, Brazil. He's graduated in electrical engineering in Rio de Janeiro in 1963 and received his master's school and PhD degrees from Massachusetts Institute of Technology, MIT in USA, both in electrical and engineering and material science. He was one of the founder and first chairman of the Physics Department of the Federal University of Pernambuco, UFPE, in Recife, Brazil, where he is currently full professor there. He has held 2 appointments as a visiting professor at the University of California and Santa Barbara in USA. His publication record encompassed over 280 scientific papers in International Journal on Dynamic Excitation Phenomena in magnetic materials, magnetic nanostructure, and Spintronics. According to Google Scholar score since 2016, he has 18,076 citations. The last year, he published the book Fundamental of Phononics. His scientific activity have evolving and interrupted alongside his numerous position in science management, namely as Dean of Center for Exact Science of UFPE, Scientific Director of the Pernambuco Science Foundation, Secretary for Science and Technology Pernambuco, President of FINEP, is the main federal agency for funding of science and technology in Brazil between 2003 and 2005, and Minister for Science and Technology of Brazil between 2005 and 2010. He has supervised more than 40 master school and PhD students, and is a long-standing member of several scientific society and recipient of several prizes and awards in Brazil and abroad. Today, in the series of webinar on magnetism, Professor Sergio will share with us his experience in spintronic topics, which all entitled Spintronic Fundamental and Recent Development. Before to start the presentation, who are connected by Zoom, please mute your microphone. Thank you very much. So welcome, Professor Rezende. You can now start your presentation.
Thank you, Oscar. Thank you, Paola. Thank you, all the organizers. And thank you for organizing all these seminars. This is very important for Latin America. Very important for people to get to know what the others are doing, and eventually to increase the collaboration within Latin America. Well, all of us have some interaction with the North, but we need to enhance the interaction between ourselves. So let me show my slides. Oscar, do you see the slides, please?
Yeah, yes, I see. It's okay. Yeah.
Okay, thank you.
Okay.
So as Oscar mentioned, this is the title of the talk. The initial part would be for people who don't work with Spintronics, so very elementary. And then I'm going to show some results obtained in our group. But first, let me show you briefly where we are. Recife is in the northeast coast of Brazil. We are about 4,000 kilometers from the Amazon, a very important region in Brazil. And as all of you know, the current government doesn't care about the Amazon. They are not doing what they should be doing, which is to take care of the Amazon forest, which is also shared with other Latin American countries. This is a current problem of Brazil, and as all of you know, we have a government that is terrible in all aspects. In the environment, in science, the science budget has been cut a lot. In health, we have one of the worst situations with the pandemics worldwide. We've been working in magnetism in Recife for 50 years. And in the year 2000, we were the host of the International Conference on Magnetism. Perhaps some of you were here at that time. And our group is at the Federal University of Pernambuco. Here are some views of the entrance of the campus, of Convention Center, and this is the view of our center, Center for Exact Sciences, that has 4 departments. Our department, Physics department, is one of them. And in our department, we have a magnetism group. Here are some photos of some colleagues and students involving working with several equipment. I'm going to be showing some results obtained with some of these equipment. And of course, a very important one is the sputtering deposition system that we use to make thin films. Well, Spintronics is the physics of and technology of phenomena that make use of the electron spin to perform new functionalities. In a way, the spin is a natural carrier for digital information, because we could say spin up means 1, spin down means 0. So it's a natural carrier, while the charge of the electron, that is negative, itself, it doesn't have 2 sides. And one asks, why this spin is not important in conventional electronics? The reason is that conventional electronics, the size of the materials is much larger than the mean free pair. So the electrons undergo many collisions in going from one side to the other, and in the collisions, the electron loses memory of the spin. However, if we make a multi-layer with layers that have a thickness of a few nanometers, an electron moving across the layers, in one layer, the electron is not does not go collisions because the layer is very thin. So the electron motion or the electron properties can be controlled by the spin. So the dimension of the sample is smaller than the mean free pair. We can have spin-dependent transport. The first important spin-dependent transport was discovered in 1988. This is the first paper reporting the giant magnetoresistance. The first author of the paper, Mario Babiš, is our colleague at the Federal University of Rio Grande do Sul. Mario was born in Argentina, but he went to Porto Alegre when he was very young. He studied there, he got the PhD there, and he was working with Albert Fert in Auxerre when they made these seminal experiments. They used a multi-layer in which between 2 magnetic layers there is a coupling with the opposite sign. So with no applied magnetic field, the magnetization in one layer is pointing left, the other is pointing right, left, right. And then when the electron goes to the multi-layer, the resistance is high. And then they apply a magnetic field in the plane of the multi-layer. And when the magnetic field is large enough, all magnetizations are pointing in the same direction. And then they observe this huge variation in the resistance, about 50%. They call giant magnetoresistance because magnetoresistance is a property of any ferromagnetic metal. But the magnetoresistance of a wire of iron or nickel is less than 1%, very small. And they found a system that has 50% variation in the resistance to the magnetic field. Well, this discovery was used to make a GMR read head for magnetic recording, a spin valve sensor. In this spin valve, there is a magnetic layer that is pinned, that is fixed, has a direction fixed by the contact with the antiferromagnetic layer by means of the exchange bias phenomenon. Then there is a copper or a low resistivity metallic layer. And here there is another magnetic layer which is free. So when the magnetization of this upper layer, which is free to move, points opposite to this, electrons move here, undergo collisions at the interface. Collisions occur at the interface, and the collisions are spin dependent. So the resistance is high when the magnetization is in this direction, and it's lower when the magnetization is in this direction. And this can be used to make a GMR sensor. The GMR sensor became very important starting the year 2000 because the magnetization, because the resistance of the sensor is sensitive to magnetic fields, not to magnetic flux. The traditional GMR, the traditional reading head was based on the Faraday effect, Faraday induction. But the Faraday induction is sensitive to flux, and flux need volume, need area. So by using a GMR reading head, it was possible to decrease the size of the bit, and this was very important to increase the capacity of hard disks. This is a long scale plot, and this is the year. And as you see, with the GMR, it was possible to make the bit smaller, and the reading head smaller and smaller, and this led to what we have today, hard disk with terahertz capacity. This important discovery by Frecht that I mentioned was also made independently by Peter Greenberg, and both of them received the Physics Nobel Prize in 2007 because of this important discovery that was gave birth to the field of spintronics. So during the 90s, the main investigation in spintronics was directed to understanding properties of single films, the exchange bias effect, the interlayer coupling between layers, the GMR, spin valve phenomena, magnetic spin transfer torque, which is an important phenomena which I mentioned at the end of the talk, magnetic tunneling, and the newer areas involve spin current, spin caloritronics, insulator-based spintronics. I'm going to give very brief information for those who are not familiar with the effects in this topic, also in spin caloritronics, and I'm going to also to give some example of our work in the new frontiers. The new frontiers are basically spintronics in quantum materials. I will not have the time to talk about them. Antiferromagnetic spintronics, I will also not have the time. I will prefer to speak, to mention about some of our recent results in spin phononics. So, as I said, very basic concept. This is a very simplified illustration of the charge current in a metallic layer. It spins with, electron spins in the opposite direction. They move in the same direction. Of course, I'm neglecting collisions here. And they carry a charge current. So there is a charge flux with no spin flux. However, if electrons with opposite spins move in opposite directions, there is no charge flux, zero charge flux here, but there is a spin flux. We can either say that we have spin up to the right or spin down to the left. Spin down to the left has the same effect as a spin up to the right. This is analogous to what happens in a semiconductor, where electrons moving in one direction, they produce a charge current that adds to electrons moving in the opposite direction, so to holes. So electrons and holes move in opposite direction, they produce charge in the same direction. Here, electrons spin up and down, moving in opposite direction. They produce a spin current, not charge current. And the spin current produces a torque. The reason is that the spin current is actually angular momentum per time per area. And we know by Newton's law that the derivative of the angular momentum is a torque. So if the spin current enters in another material, it can transfer torque to the other material. And this torque will act on the spins, on the magnetization, and this has applications, commercial application in the magnetic random access memory that I will not have the time to talk here. One very important fact was predicted in 1971, but it was rediscovered in 1999 by Jorge Hirsch. Jorge Hirsch is Argentinian, but has been in San Diego for a long time. Hirsch didn't know the work of Diakonov-Imprel, and he coined the name spin Hall effect. The name that Diakonov-Imprel had given was a complicated name. The idea of Hirsch is the following. If we have a charge current moving to the right, and the charge current has spins up and spin down, spins up, if the material has a collision which is dependent on the spin-orbit coupling, electron spin up will move up and electron spin down will move down. The reason is that if they move up, they have orbital angular momentum in one direction, and if they move down, they have orbital angular momentum in the other direction. So if the scattering is sensitive to L dot S, electrons would spin in one direction, will go up, and the other will go down. And as you can see here, here we have a spin current. So a charge current in this direction produces a spin current in the perpendicular direction, and they are related by this expression. Sigma is the spin polarization, so sigma cross JC gives the spin current, and theta spin Hall is a parameter. If we write JS and JC in the same units, theta spin Hall is an adimensional current. And platinum, a very simple platinum layer, has a spin Hall angle of 0.05, which means 5%. 5% is a big number because we have 10 to the 23 electrons moving here. And 5% of 10 to the 23 is 10 to the 21, a very large number. Now, today we know composite materials that have spin Hall angles of the order of 50%, or 0.5. 0.5 means half of the electrons in the charge current will produce a spin current. So this is an important effect. It took 4 years for this effect to be verified experimentally. 3 years later, an international team made another prediction. The generation of spin current by the spin pumping effect. Bratas, Terkovignac, Bauer, and Halperin made a theory by which if we have a material undergoing ferromagnetic resonance, the ferromagnetic material, this material will pump spin current into a non-magnetic layer deposited on top of this layer. And this is a spin current. This spin current diffuses and decays exponentially in a length which is the spin diffusion length. So spin precession also produces spin current, and they derived an expression for the spin current density in terms of the magnetization dynamics, and this is a parameter characteristic of the interface. Spin mixing conduction is a measurement of the efficiency of spin current transfer. So how one can do an experiment like this? Very simple. We have a bilayer sample here. We have a microwave generator that produces a radiation that goes to the sample. This sample is placed between the poles of a magnet, electromagnet, and we observe the response, the reflection, detect with the microwave detector. And if we do a fMR experiment with a film of permalloy, there are also modulation coils modulating the field to increase the signal to noise ratio. This is the derivative of the ferromagnetic absorption of the permalloy film. Well, my colleague Antonio Azevedo with students, and I was involved in other things at the time, but I was following the experiment. Antonio had the idea of having a tri-layer and putting two contacts at the end of the tri-layer. Then they did fMR measurement, and here's the absorption derivative. But then they measured the voltage here, and lo and behold, there is a voltage that has the shape of a Lorentzian line typical of the absorption, right at the position of the fMR signal. And they measure the voltage as a function of the microwave power. And they also measure the voltage for different materials. Some materials had a larger voltage, copper had a very small voltage. All this is quite well understood today. The reason why tungsten, tantalum, and palladium has a much larger voltage than the copper is that because they are materials that have collisions, they have large electron angular momentum, so the spin orbit coupling is large. And unfortunately, we could not understand well all the phenomena. We realized that there was a spin pumping going on. We said that this is a proof that there is a pure spin current as predicted by Bratas, but we could not explain how this spin current produced a voltage. And the explanation is actually simple, once you know it. It's the inverse spin Hall effect that Hirsch had very briefly mentioned in his theoretical paper that we were not aware of, because it was a theoretical paper with some crazy ideas, so we didn't read the paper in detail. The inverse spin Hall effect is very simple. Electrons with this opposite spins moving in opposite directions. Now they will produce a charge current and a voltage because they are moving in opposite directions. So the angular momentum has to have opposite signs because the spins have opposite signs, and then the electron go in the same direction. So the explanation that we could not realize is the inverse spin Hall effect. Spin current is converting charge current, and the expression is the same that I showed before. The charge currents given by the cross product, of course, now with the opposite, with the two in the opposite position. The spin Hall effect is a very important effect. It's still a subject of study, and there are a few review articles. This one by Axel Hoffman, 2013. This one in Reviews of Modern Physics in 2015 by this international team. And this effect is very important because it converts spin current into electric current. So this is an important way to bridge spintronics with electronics. There's a third means to produce spin current by the spin-Seebeck effect. The spin-Seebeck effect was discovered by Saito. That also was the person who explained the spin pumping experiment. What they did was to have a film of permalloy. They apply a temperature gradient. In other words, there is a heat current here. The temperature gradient produces a spin current. The spin current enters in this small platinum strip and leaves the small platinum strip, and then the spin current produces voltage. They measure the voltage, and the voltage varied with the temperature difference. So they show that heat current produces spin current. And throughout the rest of the talk, I'll be talking about a very important material for all these effects. Yttrium iron garnet. Yttrium iron garnet, such an important material for insulator spintronics, is a material that has 20 spins per primitive cell and 40 spins per unit cell. Despite this complicated structure, YEG, which is a ferrimagnetic insulator, has very small magnetic damping. And it was used in the studies of propagation of spin waves in the 60s and 70s, chaotic phenomena in the 80s and 90s, Bose-Einstein condensation of Magnums, and more recently, insulator spintronics. I'm going to speak about some effect on insulator spintronics. YEG has applications in microwave devices and also in optical devices. Well, Saito also discovered a unique effect. The spin-Seebeck effect that they call longitudinal in ferrimagnetic insulators. So what the experiment consists in having a YEG film, a very thin film of yttrium iron garnet. On top, they deposit a platinum layer, and then they apply a temperature difference. And when they apply a temperature difference, there is a voltage. The voltage is large, see, microvolts. It is easily measured. As they increase the temperature difference, delta T is the temperature difference, the voltage increased in one sign, and then if they reverse the magnetic field, the voltage increases with the other side. They call this longitudinal spin-Seebeck effect. Immediately after they discovered the spin-Seebeck effect, this international team proposed a theory for the spin-Seebeck effect. A theory for the Magnum-driven spin-Seebeck effect. The theory is based on the following. This is the ferromagnetic material. This is the platinum layer. And they showed that the magnetic system, the magnons in the magnetic material, have one temperature. They call temperature of the ferromagnetic magnons. And at the platinum, they have a different temperature. So the difference in temperature creates an accumulation of thermal magnons in the ferromagnetic side, and the thermal magnons produce spin pumping, and the spin pumping creates a spin current here at the platinum strip, and the spin current is converted into a current by the spin Hall effect. This requires the temperature of the magnons in the ferromagnetic material to be different than the temperature of electrons and phonons in the platinum layer. Well, we started doing experiments with the spin-Seebeck effect in yttrium-ion gallium. And then we were not very happy with that theory. And then we already knew from a paper by Zhang that spin waves in insulators, they carry spin current. This is a view of a spin wave. If we have magnons, the spin waves are quantized. The quanta are called magnons. If we have magnons above equilibrium, we have what is called the excess magnon number. And Zhang in 2012 showed the excess magnon number that can be integrated, and this produces a magnon accumulation in the material, and which is proportional to the chemical potential, and the magnon accumulation produces a spin current. Look why this is a spin current. N is the number of magnons, Vg is the group velocity of magnons. If we multiply this by h bar, we have angular momentum. Angular momentum per unit time, per unit length. And then if we divide by V, we have per area. So this is angular momentum per unit time, per unit area, which is current density. So one can write the spin current density in terms of the magnon accumulation. I'm showing this because I'm going to use this in two of the effects that I'm going to show shortly. Yttrium-ion garnet has, as I said, 20 spins per primitive cell, so it has 20 magnum branches. One of the branches is the acoustic mode. And this is a good approximation for the magnum dispersion relation of the acoustic branch. Has frequency of terahertz, but vary from 0 to 8 terahertz. So we made a model for the longitudinal spin-Seebeck effect. The model is this. The temperature gradient, in the same way that a temperature gradient creates a motion of phonons to transport heating, or a motion of electrons, it produces a motion of magnons. Magnons are quasi-particles. And one can calculate this motion using the Boltzmann transport equation. So magnons move by the thermal gradient, they accumulate at the interface, and they produce spin pumping. The spin pumping produces a spin current in the metallic layer, and by the inverse spin Hall effect, the spin current is converted into a charge current produces a voltage which is detected. This is the basic idea. So we calculated the Magnum current. I had showed the expression before, using the Boltzmann transport equation, also the diffusion equation. We have an expression for the spin current density, and then we can, from this, calculate the charge current. The charge current is given now using the conversion from spin current units to charge current. We have to multiply to 2U divided 2E divided by H bar. We find the voltage. So the voltage can be written in terms of parameters which are known: resistance, the width, spin Hall angle, spin diffusion length, and so on. And then we compare our theoretical model quantitatively with experiment. These are experiments that we did in the laboratory with several colleagues, Fernando Machado, with Antonio Azevedo, with colleagues that now are at the universities. So we made spin-Seebeck experiments at low temperatures. And the theory given by this expression fits quite well the experimental measurements. This was published in 2014. And of course, then there was some discussion in the literature, because we proposed that this is the model. The model that I mentioned before had no comparison with the experiment. But of course, there is always a debate who is right. And then just last year, I mean this year, 2021, this paper came out by a Spanish group. Several important researchers like Manuel Ibarra, quantification of the interfacial. The interfacial mechanism is the one that I mentioned before, and bulk contribution to the longitudinal spin-Seebeck effect. So what they did was to calculate the change in temperatures at the interface, which is the important parameter for the interfacial mechanism, and the change in temperature in the bulk and in the substrate. And then I don't have the time to go into their arguments. They show that the bulk and the interfacial contributions, they vary with the thickness. The experiments in Yale were done with films of 1 micrometer. So 1 micrometer, we are far out in this plot. But even here, at 80 nanometers, they show that most of the contribution arises from the bulk model, not from the interfacial model. So they managed to disentangle the bulk and interfacial contributions, and they, according to our results, bulk Magnum accumulation dominates the spin-Seebeck effect in the range they studied. But the interfacial component is not by no means negligible. But if we go to 1 micrometer, I'm convinced that the interfacial component is completely negligible. So we're very happy with this recent paper that I think puts an end to the controversial. Both importance, both effects are real, but for thick samples, the bulk model dominates. I have, according to my watch, 20 minutes, and I'm going to devote 10 minutes to each phenomenon here. First, the phonon spin Magnum phonon conversion experiments. Well, it's well known that photons have spin. Circularly polarized photons have spin. This was demonstrated by Sir Chandrasekhar Raman, who was Sir, Physics Nobel Prize in 1930. He made the experimental proof of the spin of photon. Now, the question is, can phonons have a spin? So we started doing experiments to convert spin waves into elastic waves, into phonons. Here is an illustration of spin waves, an illustration of an elastic wave. And one asked, can a magnum be converted into phonons? Well, it's known that magnums can be converted into phonons for a long time. This was experiments of magneto-elastic waves were done in the 60s, but they had never been done in films. The basic idea is that the spins interacted with the angular momentum by means of the spin-orbit coupling, and the angular momentum are connected to the ion motions. So the spin precession produces lattice vibration. And there is an interaction called Magneto-Elastic Interaction that involves the magnetizations, the displacement of the ions, and a constant here that says how big the effect is. Well, one can use this expression, I don't have the time to do it here, to show that magnons interact with phonons near the region that the dispersion relations cross. This is the dispersion relation for phonon, dispersion relation for magnons. Where they cross, they interact. This is the magneto-elastic dispersion relation obtained with the Hamiltonian that I mentioned. And the fact is that they interact and they become apart because of the interaction. Like two oscillators that interact, their oscillation frequencies are different. So here, an excitation here is a magnum, and here is a phonon. While an excitation here is a phonon, and here is a magnum. So we ask, can we convert a magnum into phonons? For this, we show this dispersion relation in a very large scale, in a bigger scale, log scale. And this is the same plot going up to 10 to the 6 wave numbers. And then magnums are excited by microwaves. So they have a small wave number. At most, the tail of the wave number is 10 to the 2. So to convert a magnon into a phonon, we need to break either conservation of momentum or conservation of energy or both. Because to change K, we need to have, we cannot change K with momentum conservation. And we cannot change energy with a static magnetic field. So the early experiments done in the 60s used bulk samples. In a bulk sample, the boundary of the sample creates a demagnetizing field, and the internal magnetic field varies in space. If we have a film of yttrium iron garnet and we apply a static field of an electromagnet, the field is completely uniform. Now, if we use two small rare earth magnets, producing a field in the same direction as the external field, the field varies along the film. Here is the square here denote measurements made by a spin probe, a Hall probe. This is the dimension of the sample. So within the sample, the field is very well approximated by a polynomial, by a polynomial expression, very simple. This is the internal field. The internal field is given by the sum of the field of the electromagnet and the sum of the field of the two magnets, and it's non-uniform. If it's non-uniform, it doesn't conserve momentum. So if we excite magnons, and we excite magnons with small wave numbers like here, the magnons will propagate towards the other end of the film. And as the magnum propagates along the film, the magnetic field decreases. So if the magnetic field decreases, the magnum curve goes down. Notice that the frequency of the excitation, which is 3.4 gigahertz, the frequency is fixed, but the wave number varies because momentum is not conserved. So here is the excitation, and here the excitation is a phonon. So we can convert a magnum into a phonon, and then the phonon propagates, and again it becomes a magnum. The magnum produces a magnetic field and radiates. So if we place an antenna here, we measure the radiation, and we know from the calculation that in the path from here to here, the magnum at one interval of time was a phonon. We are trying to do an experiment by placing in the middle of the sample a transducer to detect the phonon directly. But it's not very simple to make a transducer. We have not been able to make one at the point. So how we know we have a phonon? We know because we are following the wave number of the excitation, and we have the theory. We made measurements with brilliant light scattering. A laser shines on the sample. The light is scattered backwards from the sample, goes through an analyzer, a lens, and goes into a Fabry-Perot interferometer. So when we have the Stokes scattering, that means a scattered photon has an energy given by the laser photon minus the magnum energy. We detect, we see a peak in the brilliant scattering that corresponds to the Stokes peak, to the left side of the laser line. This is the laser line, and this is a small shift due to the magnum. The frequency corresponds to the frequency of the microwave generator because we're exciting the sample with an antenna. And we also have anti-Stokes, and the anti-Stokes gives another peak. So the experiment consists in measuring the size of the peaks, Stokes and anti-Stokes, with this assembly here, but using a sample that we can change the angle of the sample. Now, momentum is conserved in the sample, in the plane of the sample here. And in this way, the momentum of the excited, of the detected excitation varies with the angle of the mirror. So by changing the angle of the mirror, by tilting the mirror, we can change K. So we change K, and we measure the peaks. When we have a peak, of course, when we change K, we're going to have peaks only when the magnetic field is at the right value, so that the dispersion relation is matched. So by varying the angle, we vary the wave number. The first plot we made was a plot with the angle, but then we convert into wave number. And the dots are measured peaks with magnetic field for which the peaks are higher at maximum. And the red curve is the theoretical curve obtained with the Magnum-Phonon coupling. If there was no Magnum-Phonon coupling, if there were no Magnum-Phonon coupling, the line would be this dashed curve. So we know that it has become a phonon because the solid curve was obtained with the Magneto-Elastic dispersion relation. Now, we measure the polarization of the light scattered in this region here. In this region, we know we have magnons. And this is the angle of the analyzer, the orientation of the analyzer. Look at the amplitude of the Stokes and anti-Stokes peak as I change the angle of the analyzer. It almost doesn't change. So the polarization of the light scattered by magnons is circular. Light scattered by magnons is circular polarized. This is known. This is well known for 40 years. And it is expected because magnons correspond to spin precession. Spin precession scatters light with circular polarization. But we know that scattering of light by phonons, thermal phonons, is linearly polarized. So let's see the polarization of the phonons detected here. We have shown this, and now we did the same thing for this point here that corresponds to a phonon. And we also obtained circular polarization. So the conclusion is that the light scattered by phonons is also circularly polarized. We also did an experiment by placing a quarter wavelength plate to convert the circular polarized light into linear polarization, polarized light, to make sure that it was circular polarized. So the conclusion of this is that it's possible to generate phonons by the conversion of magnons in a non-uniform magnetic field. The light scattered by phonons generated by the Magnum-Phonon conversion has circular polarization. So phonons generated by the Magnum-Phonon conversion have a spin like the photons. And this was published in 2018 in Nature Physics. The last point, 10 more minutes, very quick. A more recent experiment involving phonons. I'm going to be very brief because I'm running out of time. Several years ago, this team made experiments that they show that one can do spin pumping by elastic waves. See, the spin pumping that I showed was made by ferromagnetic resonance, magnetization. They showed that using elastic waves, they use a transducer, lithium niobate transducer, and then they have a cobalt film and they have a platinum layer, and the elastic wave produces a spin current, in other words, spin pumping. And they did this by measuring the delay of the wave. So this is the pulse injected in transducer, and this is the delay of the acoustic wave, surface acoustic wave, SAW. When the magnetic field is in one direction, they have a positive voltage. When it's in the opposite direction, they have a negative voltage. So they demonstrated spin pumping. So very recently, we observed the reciprocal effect. By chance, we're not looking for the effect. The experiment we did used a YEG film, a platinum strip. We pass current in the platinum strip, but it's not only platinum. It's platinum, silver, platinum that has a very large spin Hall angle. This is the material that has a spin Hall angle of 50%, 50%. So we pass a current here. The current creates a spin current in the egg film. Yes, the charge current produces a spin current in the egg film, and we wanted to see if the spin current produced a torque on the magnetization, on spin waves. The idea was to try to see magnums driven by the charge current by means of the spin transfer torque. So first we did the experiment with no current. And then with the Brillouin scattering, we see a peak due to magnum with a frequency that varies with the magnetic field, and a peak due to phonons. How do we know this is magnum? We change the magnetic field and the frequency varies. So this is certainly a peak due to magnums. So here is the same spectrum I showed here, same one, but now I'm going to change the scale. I'm going to increase the scale to 1000 here. So with no current, we don't see the peaks because the peaks are down in the noise. But then we apply a current with some magnetic field. And then we increase the current. And a peak at this frequency increases up to a point where the current produces heating, and then there is no more, it doesn't increase anymore. So what we did was to vary the magnetic field. Well, here's a plot of the BLS intensity as a function of the current, intensity increasing exponentially here. And then we vary the magnetic field. No change in frequency. So this peak is not due to magnums. We could not find the effect we're looking for. So what we did, we changed the thickness of the egg film. This experiment was done with the egg film of 154 nanometers. So we made the film thinner. We have another the egg film thinner, and we measured the same effect, but now at a larger frequency. Here the frequency was 8 gigahertz. Here the frequency is 13 gigahertz. We know that phonons resonating somewhere will have larger frequency if we decrease the thickness. So again, for this other film, we saw no change in magnetic field. So we concluded that the peak was not due to magnums, was due to phonons. And then I will not have the time to show, but the idea, after 2 years, we realized what was going on. The charge current is converted to spin current in the non-magnetic metal. The spin current flows into the egg film, and in the egg film, and the current is the one that we know how to calculate, the same calculated like in the specific effect. Magnum accumulation, we calculate the spin current. But then we have the Magneto-Elastic Interaction. In the Magneto-Elastic Interaction, we have a term that has one magnum being destroyed, one photon created, in another phonon created, and another magnum created. A two magnum, one phonon process. And this is the expression for the vertex of this interaction. So we use this to calculate the change in the number of phonons using first order perturbation, simple perturbation, and then we calculate the parameter that gives the exponential increase in the number of phonons. This parameter involves the Magneto-Elastic Interaction, and the Phonon and the Magnum parameters. This is the Magnum accumulation, and when alpha is larger than the Phonon damping, the Phonon population grows exponentially. So there is a critical current for the Phonon pumping. And the calculated critical current is of the same order of magnitude as the measured one. We calculated 50 milliamps, which is the same order of magnitude. How about the frequency? Why the frequency changes? Because there is spin current only in the egg film. If we decrease the egg film, the size will decrease. So by doing the Fourier transform of the Magnum accumulation, the larger film has a smaller k, has a peak in a smaller k than the thicker film, than the thinner film. And we found that the peak is such that the wave number is, that the wavelength is about 3 times the thickness of the film. And this is also explaining the thickness. So conclusion, it's possible to generate phonon by spin current in ferromagnetic insulators. The process is the Gonzaga reciprocal of the spin pumping effect by elastic waves. The effect is explained by 2 magnums, 1 phonon process produced by the Magnum spin current. Well, phenomena involving Magnum-Phonon interaction open new possibilities for investigation and application of Spintronics. The experimental paper was published in January this year. When we published the experimental paper, we were still working on the theory, and then we worked with the theory, and the theory was published in Physical Review in April. So, to conclude, Spintronics is opening new frontiers with the discovery of exciting phenomena involving charge, spin, and heat current, offering good opportunity for basic research and technological applications integrated with electronics. And this is a commercial of my book that Oscar mentioned. I was very happy last year with the publication of this book by Springer that explains the basic. It's a book intended to be a textbook for graduate students working in magnetism. And here is some of my colleagues, Roberto Rodrigues Soares, who is in Chile, at PUC in Chile, Fernando Machado, who is expert in low temperature work, Antonio Azevedo, José Holanda, Joaquim Mendes were involved in the work that I showed. And this is a view of downtown Recife in Pernambuco. Thank you very much for your attention.
Okay. Thank you very much, Sergio, Professor Sergio, for great and excellent presentation. Now we open the question session. Let me check the chat if there are some questions.
To make the question, you can open the mic or you can use the
chat.
Lift your hand feature.
Yeah. Maria, is there a question in YouTube?
I'm checking now.
Okay, thank you.
We have some delay to the YouTube, so probably we will have to wait a little bit.
Okay.
But if someone here now have any question, you can open your mic and do your question.
Yeah, well.
You can make your questions in Spanish or Portuguese too. There's no problem.
Sergio, I have a question. In the interface between ferromagnetic insulator and normal metal is important in the spin pumping, yeah? the temperature also in the interface also. My question is rawness and surface defect on ferromagnetic insulator are important in longitudinal spin-Civic effect?
Yes, Oscar. A few years ago, a German group made experiments, several experiments, in which they have a lithium iron garnet film that they use different systems to make corrosion. Yes.
Okay.
And they measure the size of the defects, and they measure the effect as a function of the surface roughness. So roughness produces scattering, and it decreases the spin mixing conductance. I showed a quantity G, which is called spin mixing conductance. The spin mixing conductance decreases as the roughness of the surface, the interface increases. So all effects that depend on the transfer of the spin current to a metallic layer, they get worse if the interface is rough.
Okay, thank you. Thank you. Well, anyone have question?
I have one philosophical question, if you allow me, since you are a big celebrity here in Brazil, and you know, well, the government. What do you think about the science from now on, now that we have the pandemic, and what's your vision of the science here in Latin America? What's our future?
I mentioned in the beginning that in Brazil, the situation is horrible because our government doesn't care for science. They say explicitly they don't care for this. The situation is not so bad in Brazil for one reason. The state in Brazil that concentrates 35 to 40% of the research is the state of São Paulo. And São Paulo has a state science foundation that today has more funds than the two federal agencies together. So you, Maria, in Campinas, are not in a bad situation because you have FAPESP. In Pernambuco, we have FACEP, which is also very important for us. But the funds of FACEP are not very large, like in FAPESP. But overall, we are all very concerned. And the situation would be even worse if we did not have our Sociedade Brasileira para o Progresso da Ciência, SBPC, which is our big society for science, has been done a terrific job with the Congress to avoid an even worse situation. SBPC was able to promote several acts and mobilization and so on, and Congress has been supporting science contrary to the federal government. And of course, this is a problem of the whole of Latin America. One government comes, supports science, another one comes, doesn't support science. Argentina just suffered this. The previous president, Macri, extinguished the Minister of Science and Technology. Now Alberto Fernando created it again. So our countries, for different reasons, of course, they suffer from this. But overall, along the time, despite the fluctuation, the situation is improved overall.
Do you think we will have some boom in the theoretical physics, like simulation or something like that? Because it's quite hard now to enter in our labs and do the science inside the labs and experimental physics. What do you think? Yeah. Maybe the theoretical part?
I don't know if I would call a boom, but certainly there will be more theoretical papers in the last, in recent times and the future time. In about 2 years, we will see the difference. More theoretical papers than experimental papers. Currently, some of our students have returned to the lab. There are very few. They have returned to the labs. But some of the technicians have not returned, so they have difficulties. But gradually we are recovering the experimental. I see over here Fernando Machado, my colleague. Fernando Machado last week sent a photo to the whole group in the lab. He spent 1 full year without going to the lab. Now that has had 2 shots, he's gradually going back to the lab.
Muito bem, Fernando. Tá feliz? Obrigada, Sérgio.
Saudações, Carlos Ramos, Laura Steren, prazer em vê-los.
Eu vou tirar uma fotinho aqui para a gente colocar no...
Muito obrigado, Sérgio, por sua palestra, muito boa.
Pronto, tirei uma foto.
Obrigado, Diego.
Sergio, the couple of years ago, my student, my doctorate student, Joanna Gil Monsalve, was visiting in your lab. He was working with Antonio Acevedo. She made a lot of measurement about the ferromagnetic resonance and spin civic effect.
I remember him. I didn't know he was your student.
Yeah.
Very good. He or other student can come anytime. Anytime. We don't have many equipment, but there is we have one good thing, thanks to Antonio. Most of our equipment were built here. So we can fix the equipment. The ferromagnetic resonance system, I showed the photo. It was assembled here. The sputtering system, Antonio can dismantle and put everything back together, and the students learn with it. So we don't have many labs, but our labs are good for education.
Yeah. Thank you very much for opening your lab for my student. Thank you very much. I have a last question for you. About metal with a strong coupling, spin coupling to produce a spin current, like for example platinum. My question is, are there another some alloy useful with high spin hole angle? Do you know? Or we need only the normal method to measure.
People have done measurement. People have done measurement with alloys, and there is one interesting alloy, which is iridium manganese. Iridium manganese is anti-ferromagnetic but it's a metal. It has a spin Hall angle similar to platinum.
Oh,
So there are several materials. Our experiments were done with platinum, silver, platinum. Antonio discovered that when they put silver on top of platinum with very small thickness, the silver forms islands. And then they put platinum on top. So they have islands of silver, and the islands of silver increase the collisions. So the material has a spin Hall angle which is between 40 and 50%. Very large spin Hall angle.
okay. Thank you, Professor. Okay, I don't know if there is any one question. Maria?
No, I don't see any in the YouTube chat.
Okay. Okay.
I think, Paulo, do you want to close the session and tell us what's the next talk?
Yes, okay. Let me start my video just to say thank you very much, Sergio, for, first of all, for your lecture, which was enlightening. And I think we will need a whole session of lectures from you so you can teach us more of what you know and what you've done. So thank you, and also for accepting to give this talk in this new community that we are trying to encourage and to join. So that's again, thank you very much. And for our next talk, we are taking a winter break. So the next one will be in August. I think it's the 26th. Let me check. 27, thank you. And it will be given by Jose Luis Sanchez Llamazares, and it's about magnetocaloric materials. So I hope we can meet again soon. Have a nice winter break and stay safe, and try to get shot twice, just like Fernando. So goodbye. Thank you very much.
Okay, thank you very much.
Thank
Bye.
you.
Thank you.
Thank you. Thank you all.
Thank you, Sergio.
Bye.
Thank you.
Thank you.
Bye.
Thank you, Sergio.
Thank you all for putting Alma together. Very important for us.
Yeah.
Bye-bye.
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 Bye.
Okay.
Bye-bye.
Thank you.